So, as I've alluded in previous discussions around error and uncertainty, there's sort of one or two major axioms in all of science that you have to live by, and all science lives by, whether it's explicitly stated or not. One is nothing is certain in science. As much as an author or a scientist would like to convince you that their measurement is perfect and the conclusion they've drawn from that measurement is absolute, that's not true. Um, and the sort of second axiom there is that no measurement represents the true value, and that's really what informs the first axiom. It's impossible for us as humans, in our errored ways, to make any device or tool or measurement or mechanism or procedure or protocol that allows us to absolutely obtain a value without introducing some even minute or nuanced or subtle form of our own inherent bias into that measurement. We can't do it. It's impossible. There's no measurement that's ever been done that doesn't have some bias incorporated into it. So we actually have no idea what any true values are in the universe. As humans, we do our best just to get as close as possible to truth through approximation. And the tool that allows us to do that, or maybe not the tool, but the framework that guides us there, is this field called statistics, which is a mathematical field. Many of you have probably taken an intro to statistics course, or not. We're not going to do a rigorous treatment of statistics in this class, but we are going to introduce the utility of it in thinking about chemical systems. But really, what you learn here can be extended to all scientific disciplines. We're not going to dig into the theory, but we are going to focus on how to use the framework of statistics to think about how close we are to truth, represent certainty in data or uncertainty in data, and also draw conclusions about big populations of results from a few small samples. And what I'm alluding to there in sort of cryptic language is that as scientists, we often have a limited amount of time and energy and resources to do measurements. We can't do an infinite number of measurements. So we do 3 or 5 measurements. And how do we use those 3 to 5 measurements or 10 measurements or whatever it is to draw conclusions about the general population that those measurements are taken from? Meaning, how do we use 3 to 5 measurements to approximate the results we get from an infinite number of measurements? And that's sort of the other prong that statistics as a framework allows us to approach. So a lot of you already have an intuition, even if you don't have any formal training in the framework of thinking about things statistically. So what I have on the screen is this thing. If you ever watched The Price is Right, you saw this thing. There's a game called Plinko where they would use this thing. It's called a Galton board, named after the person who first developed it, this mathematician. But the way that these things work is there's usually a bunch of pins that are placed in a board. In this case, these are represented by these, let's make them a different color, red little dots that I'm highlighting here. And this is all constrained on a board typically. So these are like nails or they're little pins, and there's a bunch of them. And then you have a funnel up here, and that funnel is holding a bunch of small metal ball bearings, all exactly the same size and mass. And usually there's a stopper here, and we can remove this stopper at any moment in time, and we can allow these balls to sort of plummet down and blink off of each one of these little pins and then rest down below, and down below there's usually a series of containers all exactly the same width, and these containers are just clear plastic tubes, so we can allow these blue balls to fall through, and we can count up how many of the balls wind up in each one of these containers. If you've never seen this demonstration before, you may even be able to just think about this intuitively. What do you think is going to happen as these balls sort of bounce through here and they reach a point, and then they have a 50% chance of going either direction, and then they reach the next point and they have a 50% chance, and so on. In that case, it's impossible for us to predict exactly where any single ball will go because there's a 50% chance every time that it strikes one of these pins. But intuitively, we can think about maybe what the collective of these ball bearings will do. Let me toss in a simulation here. So this simulation that I'm about to run will walk you through what would happen if we allowed those balls to release. So you can see that's the port that's opening up. Those are all of the pins. Here are the balls as they're descending down through those series of pins. And what you start to see is a pattern emerge. Those are the tubes at the bottom, which will collect the balls as they fall. And you can start to see, I think intuitively, that there are more frequent balls if they fall closer to the centroid of where they were released. And we have less instances of balls, or a lower frequency of capturing balls, the further we get from the centroid of this diagram. So to complete our picture from what we started with, what we should expect to see is balls located at the center. Well, why is that? What's going on here? This is one of the major utilities of statistics, is that if we consider that the balls in which they're making their choice, not really a choice, but I'm sort of anthropomorphizing here, as they bounce off and have a 50% moving left to right, if we assume that the only thing affecting the chance that it will move left versus right is the random contribution to error, let me decrease the font size here, random error, if we assume that's all that's going into this and that systematic error has been identified and removed from the system, so we're not considering any systematic bias, meaning an error based on our own bias, but simply the randomness of the universe contributing to this, maybe slight deviations in the ball bearing size, slight deviations in the manufacturing of the pins, the temperature, oscillating over time, etc., etc. If we allow all of those random contributions here, then what we can expect is a distribution of balls or points that looks like this. And I've drawn onto this a red line here, and that red line is called the normal distribution. This is pretty incredible to think about, because much of the natural world, the scientific world, the physical world, measurements, many of those things that exist, variables that exist that are measurable, exist in a natural normal distribution, which is really fascinating to think about. The way that we think about this as scientists in measurement is that instead of a ball plinking through this set of nails or pins, each one of these balls is a measurement that we can make of something. Maybe that measurement is the concentration of a solution, and we're doing a titration. And every single blue bearing here is an example of one titration that you do. Assume you do all, I don't know how many are here, maybe there's like n equals 50 titrations here. If you do that 50 times and you've removed all systematic error, so there's only random error contributions to your measurement, what you should expect to see is a distribution of results that mirror the normal distribution. That's mind-blowing, right? Because you would think that if you did that 50 times and you were really, really good, that you would just get 50 of the identical result. You won't, because there's always going to be a random contribution to those results. What you will find is that the centroid of your normal distribution, right in the dead center here, that's your average. That's the average measurement that you made. The more measurements that you make as n increases from 50 and starts to approximate infinity, which we can't do, then your average starts to approximate the true value, or the mean, the true mean, which we denote as this Greek letter, lowercase letter mu. And so we call the average, typically we denote the average as an x bar. And so x bar is the average from your sample, which is usually a small number of n, because we're human and we can't do an infinite number of measurements. The more we do, that starts to approximate this mean value. What this is telling us is that the behavior of our system is going to behave this way whether we like it or not. It's going to be normally distributed. So there's no need for us to do an infinite number of measurements. We can do n is less than infinity because we know it's going to behave this way anyway. And so we can do a few measurements, say n equals 3 or 4 or 5, and still draw population level conclusions as if we were doing an infinite number of experiments. That's the power of statistics and why it becomes really valuable. So I'll also show you, you may be able to see in my webcam here, I have a mini Galton board that I'd pass around if we were in person. And so what I have right now is it's inverted. And so all of these ball bearings are sitting right at the base of the board. And what I'm going to do is flip the board, or I'm going to invert it. So I'm going to swing the whole thing this way, and that's going to release all those ball bearings, and they're going to fall. And so I'm going to turn this around, and I'm going to do that, and then you'll be able to watch this in real life, not a simulation. Hopefully it's not too reflective here. So we'll do that. And so hopefully you see that in real life, these ball bearings do in fact follow a normal distribution. It might be intuitive to you, but the takeaway here is that this isn't a fluke. This is just a really simple way of conveying this, but virtually all natural systems in the world, all physical and chemical measurements we will make, they're going to follow this as well. They're also going to be normally distributed. That's not to say there aren't other distributions. There are. There's binomial distributions. There's non-normal distributions. There's lots of different things. And if you go into statistics, you'll learn when and how to apply those things. And as you allow systematic error to be introduced to your system, and I'll show you an example of that, there's other distributions that we can think about too. So an example of systematic error in this experiment would be if I just tilted this whole thing sideways a little bit when I released it. So let me turn this around, and then I'm going to release it. Notice that I'm sort of off camber slightly. And look at my result of the systematic error. Right? I still have a distribution that looks fairly normally distributed, but the centroid of my result is systematically deviated from the true value. Right? That's where the centroid of my experiments lied. This is where the centroid of the true value lied. That's an example of systematic error, which can manifest just as easily in a chemical measurement as well. So I tossed in an example that's straight out of your textbook, which I think is a nice illustration of this. It's not a chemical example, but it's one that's pretty realistic. And what we're showing here, what the data is showing here, is the results of, I think in this case, this is the tests of 1,000, well, no, it's actually 4,768 light bulbs. This is real data. So this is from a light bulb manufacturer, maybe it's Philips or GE, I don't know who, but they made exactly the same light bulb. And they had almost 5,000 of them, so N equals almost 5,000. And what they did is they just plugged them into a socket and they measured how long until it burned out. Almost 5,000 times, right? It's going to take forever. And so what you see is a distribution where you have the lifetime, so how long it took until it burned out, and then the number of bulbs that fall within each one of these bins. And I think the width of each one of these bars here looks like it's about 20 hours. So if one of the results fell within that little window, then that bar would grow one notch upward. That's what this histogram is representing here. And so overlaid on top of that, again, is this normal distribution curve. That's the theoretical version of what the raw data, the underlying histogram, is representing. One of the central theorems, and it's actually called the central limit theorem, sometimes called the law of large numbers, is that as we increase n here, as n moves towards infinity in the measurement, if we could have an infinite number of light bulbs, what we'd see is this histogram, these data, would get closer and closer and closer to matching that theoretical line that is being overlaid I'll show you the mathematical function that's plotted to give you that. What's important to take away here, though, is that here the average of our sample being the 4,768 light bulbs, we call that x bar, and that's 845.2 hours. The spread of our data, meaning how far away our data gets from our average, the metric we use for that is the standard deviation, and we call that s, lowercase s, when we're talking about the sample. So again, this is relevant to the sample. As n goes to infinity, as we get closer and closer to an infinite number, then x bar, the average of our sample, begins to approximate the true value, essentially the average of an infinite number of measurements. Similarly, as we approach an infinite number of measurements, the standard deviation, or the spread of our sample, starts to approach what we call sigma, which is the standard deviation of the population. So it's really important to clarify when you're thinking about statistics that we're often doing a small number of measurements, which we call a sample. And a sample, then the reason why it's called a sample is because it's a small subset of a bigger set of infinite number of measurements that we call the population. And we use those terms, x bar, or average, and standard deviation, to draw conclusions about the sort of population level information. Okay, I don't want to belabor this point too much, but it's an important one, just to conceptualize the utility of statistics, because it's sometimes lost in the mechanics. You just do a test and then you forget what the whole purpose of doing a test and what were the baseline assumptions that you were making in doing or applying statistics in the first place. And so I want to illustrate to you the central limit theorem, which, as I mentioned before, tells us that as we do more and more and more experiments or more measurements, then our experimental distribution starts to mimic that sort of perfect theoretical normal distribution. This is a simulation. I'll provide the link in the Canvas site or elsewhere that comes from Brown University from a statistics course. And what it allows us to do is just change how many times we will sample the population. And so what you can sort of think about is this yellow bar up here is the population. That's the infinity of the universe. And then every time we go up into the universe and we grab a sample out of it, we're pulling down a number. And so the more times we go out and grab one of those numbers, we're going to see that in the frequency or the count on this bottom line. And so what I'm going to do is click sample here, and what you'll see is I'm doing, I have a sample size of 15, and I'm doing that 50 times, or drawing from the population 50 times, and what I get is a distribution that looks like that. And I can overlay onto that the theoretical distribution. You can see it's getting there after 50 draws. I could do that again, and you can start to see the shape of the distribution changing a little bit. It's starting to smooth out. We started to get a little bit more in the tails here, and I can keep doing this more and more and more. And the whole premise here of the central limit theorem is that eventually this will very closely start to resemble what the theoretical properties of the universe are. That's the utility in being able to take small numbers of measurements and still apply the theoretical framework of the normal distribution. So going back to this picture, I already told you that the metrics that really define the measurements that we conducted here are going to be the average of the sample, which is x bar, and the standard deviation, which really tells us where our central value is relative to truth and how wide our distribution is relative to that true value. And what I want to show you just as an aside is how that distribution would change if they had the same average but different standard deviations, just so you can develop an intuition for what standard deviation actually means. So if we had two different sets of light bulbs, which we don't here, but I'm just hypothetically suggesting you might, what we could have are two different distributions. In one distribution, maybe the black line here, denotes a standard deviation of 47.1 hours, which means that there's a fairly narrow distribution from the central X bar, or average, of 845.2 hours, but maybe a whole different batch of light bulbs were produced, and the distribution gets kind of squished and widens out. And that's because there's more random error contributing to the manufacture or the measurement of that lifetime, which leads to a larger standard deviation, something that's about twice as large. And so that means that the chances of you measuring a light bulb at the centroid gets smaller, because there's actually a greater chance that you're going to, in the blue line, that you're going to measure a value that's further away from that than you would in the central. So standard deviation is really a proxy for how close those measured values cluster together. And remember, we talked in previous videos that another sort of metric for thinking about standard deviation is this notion of precision, right? And when we talked about precision from a conceptual perspective, we often use the bullseye analogy, and it's no different than what we're talking about here with these light bulbs and the standard deviation, or the width of your distribution, right? Because if we have, say, a cluster of measurements that looks like this versus, let's draw up a second one here, a cluster of measurements that looks like this, which one of these will have a smaller standard deviation? Well, hopefully you'll say that the bottom one does. The smaller standard deviation would be more representative of the black line, and the larger standard deviation, the top one, would be more representative of the bottom line. And that's how we should be thinking intuitively about what standard deviation means within a sample or set of measurements. So why does all of this matter? I've sort of really hammered home this central limit theorem, which I've sort of re-illustrated here just with the terminology. So it's clear that a sample is when you have less than an infinite number of measurements, which is what reality is, and that we use x bar as an average metric, and standard deviation is s. That's sort of the width or the breadth of your distribution. And then with an infinite number, we have mu and sigma. So I told you that I would show you that there's actually a functional formula or relationship when plotting a normal curve like this, which is interesting because this is a natural phenomenon, but this is the relationship. We're not going to go into this. It's not really important for us to be able to plot this, but this is the plot to the left is exactly just punching in numbers from 0 to 1 for our values and computing the x and y components here. What's important to know here is that this is the functional relationship for a normal distribution, and you can see that it relies on sigma here and mu. Those are population parameters which we can never measure. We can only approximate. So when we put in our functional curve here, our normal distribution, we are approximating mu with our sample mean, our x bar, and we are approximating sigma with our sample standard deviation. That's what we would actually plug into this to get our own normal distribution based on a small number of samples. What's amazing about that then is we can go through and figure out the area under a certain region of the curve from a certain x value to another x value. If we can figure that out, that is known as the probability. The probability being the chance of finding the value within the range of selected values that you're computing the probability over. For us to do this rigorously would require calculus, because we would need an integral to figure out the area under this function. We're not going to do that in this class. I'm simply trying to get you to understand the power and the utility of statistics in that we're using an n less than infinity, certain number of measurements, to compute a normal distribution, and then from that n less than infinity, from a few measurements, we can compute the probability of finding a measurement. And we're doing that using sort of population level models of the normal distribution. We aren't even going to find the probability in this class. That's not important for most of the expressions and the computations that we'll do. But it's implicit that the reason why we're doing statistical analysis is built on this framework. This is the important understanding you want to take. We'll also mention that this curve here, which we call the normal distribution, also gets called the Gaussian curve based on Gauss, who was a physicist who was one of the early adopters of the development of this and its utility in doing physical and chemical measurements. So as I have alluded to many times already, the x bar is the average value. That's the metric that tells us how close we are to the true value. And standard deviation, or S for the sample, tells us really the breadth or the width of this distribution, in which case if we were to have a smaller S, then the distribution here would decrease like this, etc. Another thing to note is that based on that functional relationship of the Gaussian curve, which I just showed you the formula to compute that, though we didn't actually compute it, based on that, that model, which fits as long as we have a perfectly random contribution of error, no systematic error, then we know that at least for populations that plus or minus 1 sigma, or 1 standard deviation, away from the true value, the mean, the mu here, we're talking population level here, this is going to encapsulate 68.3% of all of the data, of all of the measurements. So let me delete this and sort of give you a sense for what that means. That got rid of my plus or minus 1 sigma. So what that would mean is that 1 standard deviation to the left and to the right of whatever our mu here, or x bar, is for the sample, if I were to sort of draw this like this and encapsulate that space, that's going to represent always 68.3% of all measurements. All measurements are going to lie within 1 standard deviation of the mean, and that's always going to be true. But that also means that as this value grows, then the distribution gets wider because you're getting further and further away from the mean. So this thing sort of gets compressed and pulled left and right. Plus or minus 2 standard deviations encapsulates 95.5% of all of the measurements. So that puts us way out here, and what's left are simply just the tails way out here, which get encapsulated if we include 3 standard deviations. So this is the power. As long as we use this model of the Gaussian distribution, which falls on the assumptions that we are only having random error contributing, and that we're employing the central limit theorem, that we're essentially drawing conclusions from populations, but we're really only doing samples of that population. That gives us a lot of information about where that data is going to lie with respect to the mean value given a certain standard deviation. So let's think about this in a real chemical application. So let's assume that, or imagine that, there are a couple different ways to measure lead in drinking water, which there are. There's many, many, many different ways. And let's say that for method A, you get some value and you measure it maybe 10 times, and you get a standard deviation of those 10 values. That's maybe like 1.1% of the mean value. This is a relative standard deviation, I should say. Relative standard deviation is simply the standard deviation divided by the mean times 100. So it's just normalizing the mean to the standard deviations, meaning 1.1% of the mean is the size of the standard deviation. And let's say maybe that method there is ICP-AES, which you're going to learn about in a few days. And let's say if we want to compare that to a sensor that I build in my research lab, which I build cheap lead sensors. And let's say that my standard deviation for my sensors are around 0.5%. So we had two sets of measurements, right? And the standard deviations for these two things are different. So we would have a set of a distribution, a normal distribution for method A, and then we would have a normal distribution for method B. And method B is going to be slightly more compressed, meaning the standard deviation is smaller than it is for A. This is telling us that if we do a bunch of measurements with ICP AES, we have about a twice likelihood, 0.5 to 1.1%, of measuring a value that lies further away from the mean value, meaning our measurements are less reproducible on the ICP AES than they are on the sensor, simply based on how those are distributed in this normal distribution. That's what the standard deviation is telling us there.